4.5 is rational functions. They're asymptotes and discontinuities. And your essential question are what are the properties, so looking for those asymptotes, those discontinuities, and graphs of rational functions. You're going to need your textbook today because I did not make a handout for you. And you're also going to want your parent graphs. So what is a rational function? We talked about these last year. And it's basically exactly what we talked about last year was that, oh, and this is from page 212. I think the definition I'm going to give you is a little bit clearer, and basically it's a ratio of two polynomial functions. So we could say something like f of x is equal to maybe n of x over d of x, right? Where your numerator is a polynomial function and your denominator is a polynomial function. And, it may also just be a constant. So we have two situations, which, let's see, I'm going to look at our parent graphs here. So we called it a hyperbola because that's what the graph is. I'm going to go ahead and write on here rational function. So with any kind of transformation, we said that we could, if we had a constant in the numerator, in the denominator, that horizontal shift would happen by subtracting some h, and that vertical shift would happen by adding some k. Well, before we do the transformations, let's first talk about just the reciprocal function. So underneath rational functions, we've got the reciprocal function, which becomes a pretty important function for us. So your reciprocal function could be, let's call it h of x, is 1 over x. Okay, so this is the reciprocal function, which is a type of rational function. And the difference between the reciprocal function is that you have a constant in the numerator. So you don't have a variable in the numerator. Okay, now with transformations, then h of x now has 1 over x minus h, right? The h being that horizontal shift, plus k, your k being your vertical shift. Okay. Let's see, there's two different types. Oh, and I should say actually, and you've got a stretch factor. So we'll put an a out here in front of this thing right there. Okay, so it may also look like this. Maybe instead of having a 1 in the numerator, you have like a 5. So that stretch factor just got multiplied to your numerator. Okay? So that's with transformations. Nothing new there. That's on your parent graphs. And what we said about this, well, actually, let me come to that in a minute. So we have two different types of rational functions. One is a proper. So let's see, we've got the reciprocal function. I'm going to put kind of a dot there. We've got a proper rational function. So a proper rational function is where you have the degree of numerator less than degree of denominator. I'm running out of room, so I'm going to abbreviate. Right, just like any proper fraction, okay? The degree of the numerator is going to be less than the degree of the denominator so that you don't have an improper fraction. Okay, so we're going to, oh, and then also, so in addition to that, you also have improper functions or improper rational functions. And that's where your degree of the numerator is going to be greater than or equal to the degree of the denominator. They pretty much get treated the same way. The only difference with an improper fraction is that you can usually divide it out to reduce it, to make it into maybe a mixed number. Okay? So nothing too new here, and now we're going to explore some of these. So let's look at example 1. And this is coming from your book, so it's page 213. So you're going to want to turn to page 213, and I will get it. I'll pull it up right here. So example 1, we have this function f of x, which is this thing right here. Now you can see that this is this is a proper fraction, rational function, right? The degree in the numerator is less than the degree in the denominator. So this is proper. This is fine. This is good. We don't divide, right? This thing isn't going to go into the numerator at all because it's got a higher degree. Okay, so we've got that function. We're going to simplify the fraction and describe what happens at the values of x that make the denominator equal to 0. And then use the result from part A to sketch a graph. Okay, so those are the 2 steps we're going to do, and hopefully you've got that pulled out now. So once again, our function is f of x equals 3x plus 9 over x squared plus 7x plus 12 plus 2. So hopefully you're thinking to yourself, well, I know what this plus 2 is, right? That's your plus k. And now I need to do some stuff with f of x. Okay, so just checking one more time what our directions were. So we're going to simplify the fraction. Okay, so let's do that first. So I see here that I can factor. And I think on the denominator I can also factor, right? Factors of 12, 3 and 4 will give me 7. Now, what reduces here are these x plus 3's, leaving us with a reduced function of 3, or that constant in the numerator, x plus 4 in the denominator, plus 2. Now, what's important, though, is that if somebody sees this function, they're not going to know that it came from this function. So it's really important that we also stipulate that x cannot equal negative 3, because if x equals negative 3, now we've got 0 in the denominator, it's undefined. So this x, where x equals negative 3, we're going to have a discontinuity there, and I'll talk about that in a minute. In addition, though, because we've got this constant over a polynomial, let's talk about some of our other discontinuities. So we know that we're going to have a horizontal asymptote at where y equals k. Okay, which means that we have a horizontal asymptote at y equals 2, because that's our k. And then we're going to have a vertical asymptote, basically wherever the denominator equals 0. Okay, so wherever, let's just say, when denominator equals 0. So we know that we have a vertical asymptote at x equals negative 4. And then this thing right here, that's a discontinuity, because x can definitely not be negative 3. And it's what we call a removable, I can spell this, removable discontinuity, which means it's basically a hole. Okay, so we're going to look at the graph of this thing right now. All right, so let's flip. Well, I need to flip my page over. I'm going to go ahead and start graphing this. So I know that I have a horizontal asymptote, at y equals 2. And I know that I have a vertical asymptote at x equals negative 4. Okay, you should know that stuff, okay? And then this is the standard hyperbola. So it's going to look like those two branches, right? It's going to look like this. Okay, and you can do inputs and outputs to figure out what those different numbers are. I'm going to go ahead and plug it into my calculator. Oh, where did my calculator go? There it is. Okay. So it doesn't matter which one you plug in. You can plug in your first one. You can plug in the second one. Let's see, 3. I'm going to do the second one, the simplified one. So 3 divided by the quantity x plus 4, and then plus 2 to all of that. Oh, and I need a better graph, better window here. Now I'm just going to go to so it looks like that, and now I'm going to use my table to help me fill out some values. Oops. Okay. So let's see, at -4 you can see I have that error because I've got that asymptote. Let's see, at -7, I believe I was at 1. Yeah. Let's see, at -6 I'm at 1/2. You don't have to be this exact, I'm only doing this one time with you guys. And so on. So it's basically going to look, it's going to curve down like this. The numbers just get smaller and smaller and smaller and smaller. Okay, the outputs do. And then on the other side of that, well, you can see at -3, I've got an output of 5. The problem is I can't have an output at -3, right? Because basically if x was equal to -3, my denominator would be 0. This whole thing would be undefined. So that means I'm going to put a hole there, or a removable discontinuity. So at -3, 2, 3, 4, 5, I'm going to have a hole at 5. And this thing approaches the asymptote, and then it comes down and approaches the horizontal asymptote as well. So let's see what else we got here. So at -2, you can see I'm at 3.5. Something like that. Okay, so it's going to look something like that. Let's see, so at 0, 2.75. Yep, that's about right. Looks good. Okay, let's make sure I answered everything here. Simplify the fraction. Describe what happens at values of x that make the denominator equal to 0. So we've got discontinuities, right? We're either going to have that asymptote, that vertical asymptote, or we're going to have a removable discontinuity. And then use the result from part A to sketch the graph, which we did. Oops, wrong thing. So this is part B. And that was part A. Okay, awesome. So that's example 1. So let's talk a little bit more about discontinuities. Okay, so we have a couple different types of discontinuities that we just touched on, right? So we'll say if the denominator is the quantity x minus c, then f of c, meaning where you plug in what c equals, is undefined. And graph has a discontinuity at x equals c. And there's two different types. So one type could be a removable discontinuity. And this usually happens whenever the, let's see, so we've got this factor x minus c. So we've got the fact that the factor reduces. So that means that there's a hole at f of c. In example 1, we had a hole at f of negative 3. Okay, so that's removable discontinuity. And then the other one is that vertical asymptote. And again, that's when we have x minus c present in the denominator. After all simplifying. So then that tells us that x equals c is a vertical asymptote. And that happened in example 1. We had a vertical asymptote at x equals negative 4. Just for you to refer to that. So those are our types of discontinuities that we can come up with there. All right, let's do another example. We're going to move on to example 2. And this comes from page 214. All right, so example 2. We've got this rational function. We're going to explain why there are no discontinuities in the graph. Well, what happens here? If I were to plug in 3, I get 0 here, but there's still a plus 1 there, right? So the denominator will never, ever, ever equal 0. Okay, so let's write that stuff down. So we've got the function f of x equals 5 over x minus 3 squared plus 1, and then minus 2. Okay, so for a, the denominator never ever equals 0. So that's why it's not discontinuous. No discontinuities since denominator does not equal 0. Okay, let's go on and explore part B now. Explain why the graph has a horizontal asymptote at y equals negative 2. Okay, well, let's think about this. What happens as x gets really, really big here, either positive or negative? So it gets really, really big in the positive direction or really, really big in the negative direction. Basically, this denominator is going to be huge, right? This denominator is going to go to a really big number, maybe 1 million, maybe 2 million, maybe 5 billion. So really, this whole number then, if the denominator is so huge and the top, the numerator, is staying the same, then this fraction right here goes to 0. Oops. So we can say then that for B, as x gets large, in the positive or negative direction, then we know the denominator gets large. Which sends that fractional part, the 5 over x minus 3 squared plus 1, sends it going to 0. So that really means that f of x basically goes to negative 2. Right? That function, if this whole piece right here goes to 0, then f of x is just going to negative 2. Hence, your outputs are only going to approach negative 2. Okay? All right, let's do C. C asks, what feature will the graph of the function f have at x equals 3? So we need to think about at x equals 3, what is happening? Oops, I keep touching the wrong one. All right, well, let's think about this. As x equals 3, so here we are, I plug 3 in for x. I'm basically going to have 5 over 1. Actually, let me go back to the original function. Plug 3 in, I'm going to have 5 over 1 minus 2. So when I plug 3 in, this is the smallest that the denominator is ever going to get, right? Because this all becomes 0. So basically my denominator, the smallest it's ever going to be is 1. So that means that that's going to be my maximum, right? My output there is going to be my maximum because my denominator is going to be the smallest ever. So it's going to be 5 divided by 1, which is 5, minus 2 is 3. Okay, so at x equals 3, we have a denominator is at a minimum. That's the smallest it can possibly be. So f of 3 is a maximum. All right, and so for D, we'll move on to that. And maybe I should write this is a local max because we're not sure exactly what this looks like. Moving on to D, the question is, sketch the graph of function f, and then verify that your sketch is reasonable by plotting the graph of function on your grapher. Is the graph concave up or is the graph concave down at x equals 3? Oops, I keep touching that. Sorry about that. All right, so we're going to sketch the graph. Okay, so this can be helpful to think of it like an input-output table. But first of all, I started at 3. I've already thought about what's happening at 3. So again, that was going to be 5 divided by 1, which is 5, minus 2 is going to give me 3. So I know that 3 is a point, and that should be my maximum. Okay, because again, that's when the denominator is the smallest. All right, well, let's do a couple other points around that. So how about I'm going to choose some easy numbers. So how about if I do 1? All right, so f of 1, 5 over, and I'm just going to do this, 1 minus 3 is negative 2. I'll square that, plus 1 minus 2. So I'm just picking arbitrary points here, but ones that look like they're easy for me to do. Because this ends up giving me 5 divided by 5 minus 2. So that's 1 minus 2, which is negative 1. So at 1, I'm down to negative 1. And how about if I do, let's see, 5 minus, how about if I do 5? Because that's going to be symmetric, it looks like, right? If I put 5 in, I'm going to have 5 over, well, 5 minus 2 is 2, square that, plus 1, and then minus 2 from that. So I get the exact same thing. I'm going to have negative 1 again. Looks like it's symmetric from there. Okay, well, what else do I know about this thing? I know that I have a horizontal asymptote at negative 2. That's my k. So I know it's not going any lower than negative 2. Actually, it's not even getting to negative 2. So the graph is going to look something where it's got to approach this asymptote, right? It's going along this asymptote. It starts to get bigger, comes up to our maximum, and then it heads back down. Something like, well, something like that. That looks pretty bad, but you get it. And then you can check that on your calculator, and you can make sure that it does match. And we know that at x equals 3, the graph is concave down.